So lenticular galaxies are sort of a halfway point between being an elliptical galaxy and being a spiral galaxy. Like the elliptical galaxies, they contain mostly population 2 stars, and they have a very large nuclear bulge, but they do have a disk. However, very little star formation happens within them. So, sort of one way of thinking about this is there are elliptical galaxies with a very weak disk, or a spiral galaxy with a very dominant nuclear bulge and no spiral arms. The last classification for galaxies are irregular galaxies. And irregular galaxies are basically those that don't really have a really nicely defined structure like the spirals, the ellipticals, and the lenticulars. Irregular type 1 galaxies do have some structure, but they generally have low mass and are disorganized in terms of star formation. Type 2s have no structure. And with type 2s, a lot of these galaxies are really the result of two collisions or mergers of galaxies that happened recently, that there hasn't been enough time for them to take a particular shape. Good examples of irregular galaxies, which are actually visible in the nighttime sky, are the Magellanic Clouds. Here we see two of these irregular galaxies, the large and the small Magellanic Clouds. Now, don't go outside expecting to see these at our location. You have to be fairly close to the equator or in the southern hemisphere to see them. But they are two of the closest galaxies to us. The Large Magellanic Cloud, again, is a type 1 irregular galaxy. It does have a central bar at the center. You can see that right here. Some weak spiral structure, but really not enough to call it a spiral galaxy. The small one, or the small Magellanic Cloud, is pretty much the same thing, just a smaller version, but actually a little bit closer to us. Let's talk about the masses of galaxies. How massive do galaxies become? Well, just like stars, galaxies come in all different masses. Most galaxies, like our own Milky Way, the Andromeda Galaxy, those are actually bigger than the normal galaxies. They're anywhere from about 1 billion solar masses to about 1 trillion solar masses. Andromeda is closer to the trillion edge, so Andromeda is about as big of a spiral galaxy as you can get. Milky Way is a little less massive. Now, elliptical galaxies tend to be more massive. They actually start a little bit lower on the scale, about 1/10 of a billion of a solar mass, up to about 10 trillion solar masses. In fact, the largest galaxies that we know in the universe are actually giant elliptical galaxies, from 10 trillion solar masses all the way up to 100 trillion solar masses. Now, we also have dwarf galaxies. Dwarf spirals, dwarf ellipticals are just smaller versions of the spiral and elliptical galaxies, as you might imagine. Now, giant ellipticals are very rare, okay? We use the designation CD for the giant ellipticals, and they're the largest, most massive galaxies known, but normally you don't see these except for in the most dense clusters of galaxies. Only when you have a cluster of thousands of galaxies do you normally see these things, and they're normally at the center of these clusters because these giant elliptical galaxies are built from the mergers of many different galaxies put together. Again, they range somewhere between 10 trillion solar masses and 100 trillion solar masses. This is a view of Perseus A. It doesn't look like an elliptical galaxy. It looks like it has more structure than that. But Perseus A, you see a lot of these tendrils of gas and dust. And it's probably the remnants of other galaxies that this huge monster has consumed. But by far the largest of all galaxies that we know of is IC 1101. Now, here's a comparison. Here's our Milky Way galaxy all the way down here, that little speck right there. Bigger than that is the Andromeda galaxy. And next to that is M87, which is as big of an elliptical galaxy as you can get before actually considering it to be a giant elliptical. In fact, some consider it to be a giant elliptical. IC 1101 is so large that if it was in our cluster of galaxies, what we call the local group, it would stretch from one end of the local group to the other end. On the other edge of the mass scale, dwarf elliptical galaxies can be some of the smallest galaxies. In this next picture, we're going to see the Andromeda galaxy, which is a large spiral galaxy, and two dwarf ellipticals that orbit close to it. So again, just like stars, you can have very small galaxies, or you can have very large galaxies. Active galaxies. Now, some galaxies were discovered to be peculiar. They would have strong radio sources and or strong X-ray sources. We now know that these galaxies with active nuclei are basically galaxies where the black hole at the center of them is actively consuming matter and therefore giving off intense jets of energy. Now, this is M87, I believe. And at the heart of almost every galaxy is a black hole. Now, you can't see the black hole in this image. That bright spot right there doesn't actually represent the black hole, but rather very dense collections of stars close to the center of the galaxy. What you can see, however, is this blue jet of material. And this blue jet is being given off by the very massive black hole at the center of this large elliptical galaxy. So, some galaxies we say are active. The black hole is actively consuming matter and at the same time beaming these streams of intense energy. Galaxies like our Milky Way are not active because at some time in the Milky Way's past, it probably cleared out all the matter or most of the matter very close to the center of the nucleus. So there's basically nothing left to feed the black hole. However, when galaxies tend to merge, one galaxy tends to consume another galaxy, it can disrupt the matter near the black hole and force more matter into it, making it active again. Basically, galaxies can be categorized, if they are active, they can be categorized a number of different ways. The lowest level of activity usually just includes radio jets. You've got an active galaxy, but it's broadcasting a little bit heavier in the radio part of the spectrum because the black hole is consuming a small amount of matter. Okay? The next level of activity would be a type of galaxy we call a Seyfert galaxy. When these galaxies were discovered, the centers of these galaxies seemed to be extra bright, too bright for a normal galaxy. We now know today that that extra light coming from the center of these Seyfert galaxies is actually due to the accretion disk around the black hole, that the accretion disk is actually outshining the rest of the galaxy, appearing to be very bright. By far, however, the most active of the active galaxies are quasars. These had such bright nuclei that, in fact, when they were first discovered, everybody thought they were stars. However, later images showed that, or I should say later spectroscopic measurements showed that these quasars were very far away with large redshifts, and we soon realized that these were galaxies. Now here's NGC 3079. This is an active galaxy. Okay? And what we can actually see at the center in this infrared photograph are these filaments of hot plasma being blown out of the center. Again, we'll go back to M87. That's a galaxy we talked about before, a large elliptical galaxy. And again, you can see that this is active. It's not a Seyfert galaxy, and it's not a quasar, but there's enough energy going on in this black hole to give off this intense jet. And again, what's powering these things? Well, as long as matter is tumbling into the black hole through this accretion disk, this disk gets spinning faster and faster and hotter, and as it does so, it emits X-rays and a tremendous amount of energy. Here we can see this lower image. Can't see the black hole, can't even see the accretion disk, but you see this thick band of clouds surrounding the accretion disk, which powers this active galaxy. Here's NGC 6251. And again, this galaxy has a very active core, has a very active nucleus, and a very bright accretion disk at the center. Now, Doppler measurements near the nucleus tell us that there's basically only one thing that can power a galaxy like this. These large Doppler shifts, blue in one direction and red in the other direction, indicate that all the matter is moving very quickly around a very compact object. And again, the only thing that could produce that is a black hole. Here's Centaurus A, another active galaxy. And this is a large elliptical, not a giant elliptical, but you can see that it has these intense dust lanes surrounding it. Very unusual for an elliptical. We don't normally see that. But we're fairly certain that these dust lanes are actually left over from a spiral galaxy that this galaxy consumed. In the infrared, Centaurus A, we can get to the next image, is a close-up of that previous image. Now, if we look in the infrared, we can see this bright spot, and that again is the accretion disk surrounding the black hole that's powering this whole thing. Now, here's a Seyfert galaxy. Again, we can see that there's some normal features here. It's got a spiral, it has spiral arms in this disk. But what is remarkable about this is the center right here is so bright it's overexposed on this photograph. Again, Seyfert galaxies have very bright centers because of the accretion disk. Another Seyfert, NGC 1567. Again, very bright, unusually bright center, not as bright arms. Not a great photograph of that, unfortunately. Looking at the nucleus of this again, we can see this hot plasma being ejected from the center. And this was taken with the wide field planetary camera on board Hubble in the infrared part of the spectrum. Now, Seyfert galaxies have very active centers, but by far the most active of all centers are the galaxies that have quasars, or the galaxies that are quasars. Now, in this photograph, we see two images. We see the image of a star. We see the image of a quasar. Can't tell the difference of them. But in 1960, we started measuring the redshifts on these quasars and found out that they were flying away from us at great speeds and therefore had to be very far away from us. We now know that the distances to these quasars are billions of light years away. And again, this is sort of an interesting photograph. We have this bright galaxy in the foreground, and then much, much further away, we have a quasar. Again, a quasar is just a very bright nucleus of an active galaxy. Some more images of different quasars. Here's one taken with a ground-based telescope. You probably would have thought that this is just a star, unless you had used the Hubble to actually see the outer bands of the spiral arms. More quasars. Again, you wouldn't want to be in a galaxy with an active quasar. These accretion disks give off a lot of X-ray radiation, and we think that quasars are sort of an early state that a lot of these galaxies went through. That as they emerged, it disrupted a lot of matter. A lot of matter fell to the center and made the nucleus, very, very active. So, these quasar phases were probably a phase during the very early part of the universe. So, elliptical galaxies, mainly old stars. Spiral galaxies also have a lot of old stars, but they also have new stars forming in their disks. Unfortunately, our universe is in a state of decline. Okay? About 3 billion years after the universe formed, somewhere around here on this chart, 3 billion years ago, 3 billion years after the Big Bang, would have been about 10 billion years or 11 billion years ago. Star population or star formation reached its peak. That stars were being created at an incredibly fast rate. And today, if you look at this curve, star formation is a mere fraction of where it was billions of years ago. So we're in a state of decline. Our universe is already slowing down. But star formation, again, is very different for different galaxies. In elliptical galaxies, we see almost no star formation today. We believe that most of the star formation happened around 2 or 3 billion years after the Big Bang, and then it stopped somewhere around 7 billion years after the Big Bang. And, that's about 7 billion years ago today. SA, SB, and SC, spiral galaxies still have star formation going on, but that also peaked a long time ago. By the way, irregular galaxies, this line doesn't represent what's really going on, but irregular galaxies are thought to have a very high rate of star formation even today. Okay. Just like we can group stars together to form star clusters, galaxies are also grouped together to form galactic clusters. These clusters of galaxies basically come in two different types of categories. We have groups like our own, what we call a poor cluster, where the number of galaxies is rather low. We only have about 50 galaxies typically in a poor cluster. And then on the other end of the spectrum, we have the rich clusters, which can have thousands of galaxies contained within their gravitational reach. Now, the cluster that we're in is called the local group. There are basically 3 big galaxies in there, or 3 good-sized galaxies in there, no giant galaxies. The largest is the Andromeda Galaxy, or number 2, and then the Pinwheel Galaxy is the next biggest. All the other members of the local group are pretty much dwarf galaxies after that. Okay? Again, 2 large spiral galaxies, 1 medium spiral galaxy, about 13 irregular galaxies, and over 20 dwarf galaxies. Now compare that to a rich cluster. Again, rich clusters have thousands of galaxies, but they also contain some of these monster giant elliptical galaxies. Good examples of some of these clusters, or a good example of a very close cluster to our own, is the Virgo cluster. We're actually part of the Virgo supercluster. So our little local group plus the Virgo cluster plus a few other clusters makes an even larger group. We also have the Hydra cluster and the Coma cluster. Now here's a view of the Virgo cluster. It doesn't look very impressive, but you have to remember, none of you, I'm going to get a chart here. Here's a breakdown, about 30 elliptical, 49 lenticular, 128 spiral galaxies, 828 dwarf spirals, 30 dwarf lenticular, about 90 dwarf irregular, and 90 dwarf irregular elliptical. So over 1,000 galaxies. And in this image here, hopefully an image is coming up, you see the Virgo cluster, but it doesn't look very impressive. It just looks like a bunch of stars. But again, there are a lot of dwarf galaxies, many of which you can't see, and then a few big elliptical galaxies and a few spiral galaxies within it. Back to M87. M87 is the big central galaxy at the middle of this. We think that its total mass is about 10 trillion solar masses, so it's right on the edge of being a giant elliptical. The interesting thing is, the bigger the galaxy, normally the more matter it has in terms of dark matter rather than regular matter. So in these rich clusters, only a small fraction of the matter is actually made of visible matter, about less than 1%. Most of the matter is actually contained within this type of matter called dark matter. Here's an X-ray image of the Virgo cluster. You can see that the plasma that surrounds these galaxies, this intergalactic space, actually is quite hot and does contain some gas. Here's a Coma cluster, or part of the Coma cluster. We can see big giant elliptical at the center. Here's a spiral galaxy, a few interacting galaxies, another spiral. Here's a view of the Hydra rich cluster. You have to ignore these two stars here. They're not really part of it. Again, spiral, ellipticals, whole gambit. And here's a very distant cluster with a superimposed X-ray map, and that shows, a lot of the hot gas that's given off by the active galaxies that remains around these rich clusters. The interesting thing is, these clusters are so massive they can actually bend light. This produces an effect called gravitational lensing that nearby clusters like this Abel 2218 actually makes it easier to see these distant quasars and galaxies behind them by bending the light. And the way it works is this. Gravity, just like glass or anything else, will slow down light and cause it to change direction. So these arcs that we see in many of these photographs are actually images of quasars and images of distant galaxies that are being bent. Here's a view of them. This is kind of interesting. These two images are quasars, which are actually optical illusions that sit behind this galaxy right here. Here you see an arc which is being gravitationally lensed. Here's a galaxy that's being lensed 4 different times. Now, galaxies can be organized into poor clusters or rich clusters. But there's an even larger collection that we call superclusters. So for instance, we're in the Virgo supergroup, which is right here, which is right on the edge of the center of this collection. Virgo supergroup includes not only our own poor cluster, but also the very large, rich cluster of the Virgo cluster. And here is an image of our local supergroup. Hard to see what's going on right here. Here's our local group, here's the Virgo group, and then there are just a whole bunch of other poor clusters of galaxies. Now again, galaxies grow by basically consuming each other. So galaxies are constantly colliding into one another and reforming as a result. So galaxy collisions are very, very important to the life of the galaxies. In fact, in about 5 billion years, we're going to crash into the Andromeda galaxy and the two galaxies will merge. This is an extreme example of galaxies. Here we have two galaxies bumping into each other, two galaxies here bumping into each other, and then more over here. So again, the result of these collisions not only builds bigger galaxies, it also triggers tremendous amount of star formation. This shows a spiral galaxy being pulled by another galaxy that's barely visible at the edge of this photograph. Notice all this blue right here, all this blue in this other galaxy. That's because if you disrupt the gas and dust, you create a huge swarm of new stars forming. Here's some more examples of emerging galaxies. You can see bright blue where new stars are forming. You can see dust lanes going from one galaxy to the other. These galaxies are slowly merging together and will probably form an elliptical. Again, more collisions. Here's a galaxy that got hit by a much smaller compact galaxy right through the center. This galaxy right here passed right through the center and produced this ripple effect that we see in this cartwheel galaxy. Here's a close-up of the cartwheel galaxy. You can clearly see there's lots of star formation, not just happening on this outer ring, but also on another inner ring that's formed. Here's the Antenna Nebula, two galaxies colliding. You see this galaxy here and this galaxy here, they're colliding. These long tails are stars that are being stripped from each galaxy and hurled into space as these long tails. But you see close up, here's the nuclear bulge of one, the nuclear bulge of the other. They're all surrounded by all this blue here. Again, mainly new star formation caused by the tidal forces of the two galaxies combining. Then some more views. Clearly, you can see very intense star formation taking place in several different regions. And very distant photos of small galaxies merging to larger galaxies. So in summary, galaxies come in three basic shapes: elliptical, spiral, and irregular. The Milky Way galaxy is one of two large galaxies in our local group, which is a poor cluster. Rich clusters can include thousands of different galaxies, and the local group is a member of an even larger collection of galaxies called the supercluster. And we call this the Virgo supergroup, or sometimes just the local group. Finally, active galaxies are galaxies that give off strong radio emissions or strong X-rays, And these can include very intense galaxies such as Seyferts and quasars. Well, that concludes our discussion of galaxies. Sorry that it came in 2 parts, but that is was due to a little technical flaw.